Okay, there we go. So today, Ted Erie is going to talk to us about linking Phreeqc with GoldSim using a Python interface. And so without getting into too much more of that, I just want to make sure that, first of all, we're going to do a sound check with Ted and also make sure you can see his screen. So I'll go ahead now and turn the time over to you, Ted.
Yeah, thanks, Jason. If you can hear me, would someone let Jason know?
Yeah, just click on that hand icon again if you can hear Ted. Okay, yeah, it looks like people can hear you, Ted.
Okay, great. Jason, I think you need to allow me to show my screen.
You're right. Thank you for reminding me. Okay, and now you can.
Okay, I guess I'll ask now, is my screen showing? You should see the top view of a small model.
Yeah, if any of you do not see, just type in a question, and also at any time during the presentation, feel free to type in a question in the chat if there's any problems or questions during the presentation, and I will always be monitoring that and watching that. But I can see it, Ted. I think we're good to go.
Okay, very good. Thank you. Well, if you're at this webinar, thanks for attending. I take it you're interested in using Phreeqc and learning more about the Python interface. On this opening screen of this model, I've written down a few things that you need to consider if you want to take this route to modeling chemistry. First of all, it's probably obvious you need to have an installation of Python. I'm using version 3.8 from Anaconda. Secondly, you should install the GSPy-Python interface from GoldSim. And you can find that at the model library at goldsim.com. That installs basically the dynamic link library that has been created. And that dynamic link library is the key component that we need to use to make the linkage actually to Phreeqc, or actually any other outside external program that you might want to use as well. So there are some necessary files that will come with that. There's instructions on how to install it with that download, and there's also a couple of files you can use to test to make sure it's working correctly. Next, you need to install the PhreeqPython wrapper. This is a wrapper which allows you to use a Python implementation of the Phreeqc software, and you can get that from GitHub. I've listed the website here. It was generated by I think the name is Abel Heinsbroek with a company called Vitens, which is a drinking water company in the Netherlands. So that's also a necessary installation. And if you have Python installed, you can install PhreeqPython just using pip. So if you're knowledgeable about Python, then that's an easy installation. Also you need to have GoldSim, and I'm using the contaminant transport module, and I'm using version 12.1.5. I think that's the most recent version. You should probably have an installation of Phreeqc and be knowledgeable how to use Phreeqc, because of course that's what's going to do all the chemistry calculations in this approach. Also at the model library, if there is an example which was uploaded last winter after I was working on this approach. Jason and I worked together a little somewhat on that, and it's now in the model library. So you can download an example of how to do this sort of linkage from that model library. And this particular example actually has both the Python approach and the C++ approach, and they are applied to exactly the same model. So you can see the differences between those two approaches if you want to go into detail on how to do the linkage. Finally, if you want to work with Python, of course, it really does help to have some knowledge about how to program in Python. I'm certainly not an expert in Python, but I have a little bit of knowledge, and that's fortunately was basically all that I needed to get this to go to work when I was developing this last winter. Like I said, I worked on this sort of last fall and last winter. I spent a lot of time indoors at my house, like probably a lot of you. So this was sort of a project that I worked on while I was pretty much stuck here doing other things as well. So I'm going to get into the model a little bit now, and I have built out a fair amount of this model so that we have a good starting point so that I don't run out of time trying to explain it. But I will build the model, and I'll try to explain the reasoning behind why I'm doing certain things as I build that model. And I'm going to scroll down a little bit now here, and I'm going to show you the conceptual model for this little example that I'm going to work on today as part of this webinar. And so there's a schematic shown here. It's sort of a conceptual model of a very simple system. I work mostly in mining type applications, so you see a lot of sort of mining related terms like waste rock and tailings. But if in this particular example, we have a pond, and it has basically 3 inputs of water. It has water coming from waste rock runoff, it has tailings water and precipitation, and it has 2 outflows, one to evaporation and then another one, which is water which is being pumped from the pond over to a tank. In the tank, we have another input of water, which I'll call mine water or mine dewatering water, which also goes into the tank. And then the tank just has an overflow where the water exits. But in this example, I'm going to apply Phreeqc in 2 places. One, for the mixture of water that's in the pond. Then I'm going to take that equilibrated chemistry that is pumped to the tank, and I will mix it with the mine water and equilibrate it again with Phreeqc. So I just wanted to show an example that you can use Phreeqc more than once in a model. In fact, you can use it as many times as you want. It does slow down the execution of the model, but sometimes in a complex system, you may need to use it a few times. I've had models where I might have 5 or 6 or even 7 different places where water is stored and mixed that I needed to have this sort of equilibration calculation as part of the model. Now, I should add that GoldSim does have a lot of capabilities to do chemical calculations. So to be honest, most of the time, I don't need to use Phreeqc. If you just use simple dilution and mixing, which GoldSim does automatically, that actually covers a lot of the situations that at least I've run into. So let's take a quick look at this model. I do have a climate container because I do have parts of the model representing precipitation and evaporation. If I go into the climate container, you can see it's pretty simple. I have a time series for precipitation. And this just has 2 years of daily precipitation data, millimeters per day, starting in 2018 and ending, let's see, the first day of 2020. So that's also the time duration for this model. It's a 2 years with a daily time step. I also have evaporation, and for the evaporation, I'm using just a monthly evap. This would be like a pan evaporation rate. And so I've got the month of the year and then the evaporation rate. The only thing that's a little bit different is I'm using a script element here to sort of spline these monthly values so that I get a smooth transition between the months for the evaporation. This approach is directly out of the model library. I think it's a model that Jason put together and had uploaded a while back. Anyways, it works really nicely, and I think it's a good way to sort of smooth out those monthly evaporation rates. For example, if I ran the model right now, If you looked at the monthly evaporation, you can see it has this blocky month-to-month time history. But the splined values smooth that out, so you get a nice, smooth, day-to-day evaporation. Okay, so that's enough for the climate. The other part of this model is the material. I'm using the contaminant transport module, so this container is automatically created. And when it's created, it creates two elements, one called water, which represents, of course, water. It has the properties of water. And the other one is the species. And in this element, there is a vector of species. And this is something that for everyone who builds the model of chemistry, you have to add. So I just use the IDs, I use the chemical symbols, or if it's something like nitrate, which has a range of oxidation states, I might put in something like nitrate, and then I put underscore n to refer to the fact that this actually refers to nitrate as nitrogen. The same with sulfate, I put it in as SO4. But one important consideration for this approach is pH is at the last position of the vector. So in your models, you might have 30 different species or 15. For the particular Python approach that I put together here, the pH has to be the last entry in this vector. And I'll get to the reasoning for that later, but what it comes down to is the fact that in GoldSim does everything with dilution and mixing. And so it can't really calculate pH very easily. So we actually don't want to use the pH from GoldSim. We actually want to get the pH coming back from Phreeqc, where it would be correctly calculated according to the effects of aqueous speciation and solubility and redox and all of those things that Phreeqc does. So I've got 21 entries into my species vector, and that is another important consideration because the Python connection to Phreeqc has to know how many entries you have in this vector. In this case, I've got 21. And again, I'll get back to that when we look at the Python code. So I'm going to go back up into the main view of the model. And next, I will go into this container called water and chemistry. And I've combined both the water balance here and the chemical balance, which is something I probably would not normally do. I'd probably put them in different containers, but for this example, it's kind of nice to see the connections between the water balance and the chemical balance. I should say a little something about the simulation settings. It is set to 2 years, so there's 730 days at a 1-day time step. And I did set up the reporting steps in case I needed them, and I'm doing those for every basic step, with annual and monthly time periods for the reporting steps. So for the inputs for the water balance, I have a tailings water inflow. This is just a time series for daily data. The waste rock runoff is the daily data as well. The direct precipitation, this is a calculation based on the area of the water in the pond. So there is a series, there's a lookup table that's contained back here in this pond configuration container, which just gives us the volume, or no, excuse me, the elevation of the water in the pond as a function of volume. And you can use that, of course, to get the area, and then I just multiply it by the precipitation to get the total amount of water hitting the pond surface. A pretty standard thing in a lot of models that I've seen. The same with the evaporation. This just calculates the evaporation and multiplies it by the surface area of the pond. No, so the pond has 3 inflows, and then it has 2 outflows, one to evaporation and one, the water that is pumped to the tank. And I'm using a pool element here because I find those to be quite flexible and quite nice to use. The pumping is based on sort of a logic I use a status element. If the pond gets higher than the maximum operating volume, which is 9 million cubic meters, then the pumps turn on. When it gets below the minimum operating volume, which is 7 million cubic meters, the pump turns off. And then I just have a pumping rate here of 3,600 cubic meters per hour. This is a big pond, so the rate is really high. And the selector element just turns the pumps on and off. So it's either on if the status element is true, and it's off if it's false. So again, if I ran this model right now, and we looked at the volume in the pond, you can see it fluctuates between about 7 million and about 9 million cubic meters. Here it goes a bit higher because the pumping didn't start until it reached here, but it took a while to catch up. And then after that, it's fluctuating between that minimum and maximum volume. Well, this water gets pumped over to the tank. And so the tank has two inflows. One, well, I'll put it over here. One is the volume coming from our pond volume. That's the pool element over here. So it's the pond volume dot pump to tank. And then there's the water coming from the mine dewatering flow. And the mine dewatering flow is just based on the monthly water table or monthly lookup table, months of the year and flow rate. And this tank, it's really just sort of a static reservoir. I set the initial and the upper bound to be the same, so that whatever goes into the tank overflows out of the tank, and then basically exits our system as it's set up here. So these things for the water balance, these elements, they all have implications, of course, for the chemical balance. And in particular, in any kind of model that you work on that involves chemistry, for each unique or different type of water that enters your system, like precip, tailings water, the waste rock runoff, the mine water, it needs to have a defined chemical composition. Now, it's probably debatable whether you need one for precipitation chemistry because, really that's sort of like distilled water. But I did have a chemistry in this case, so I put it in just to make it complete. But you can see the concentrations are really low. And a lot of these are zeros because I didn't have concentrations for everything. So I have linked this over to a cell pathway element. And the reason I do this is this sort of defines the chemical sources that are going to mix in the pond. And I'm going to go back to edit mode here before I open this thing up again. In this particular case, this cell pathway, it's a chemical source which is entering the system. So you can give it basically any volume you want. So here I've just made it 10 cubic meters. But the inventory is important. In this particular case, it's a defined concentration, which refers back to our precip chemistry. In this particular case, it's just a vector of type species. So there's just one entry, one set of values for each entry in that vector. The next cell pathway is the one that defines the chemistry for the tailings water. Actually, let me open up that element first. The tailings water chemistry, it's also a data element, but it's a matrix. So the matrix has rows of the species vector, so it has all of the chemical components in the position of rows. And then I have monthly values going across. So for each month of the year, I have an averaged chemistry. And one important thing about the chemistry when you're working with something like PhreeqC and you want to have it do the calculations is that I have run all of these chemistries through PhreeqC first to create these inputs because I wanted to have the charge balances come out to zero. Normally if you have an analytical result for chemical composition, it has some sort of charge imbalance. It might be 5% or 10%. Or maybe 15%. Well, you don't want to use that in this kind of calculation. You want to charge balance it first because you want PhreeqC to do that calculation of the effects of mixing and then the effects of aqueous speciation and redox and solubility. You want those effects to be what's controlling the pH and not Phreeqc trying to balance your pH based on changing the charge balance. So this gets around that problem. Just make sure all of your input solutions are charge balanced first. And if you don't do that, you'll get some pretty strange results. At least I've certainly made that error, and that's what I found. So if I go back to this cell pathway, again, I have just set to some arbitrary volume. I got it set to define concentration, and then it refers back to this data element with that matrix. And I'm just using the shorthand notation of asterisk or star, comma, month to pull in that data so that we have the monthly chemistries coming into this cell pathway. The cell pathway for the waste rock, it has a very similar form. Again, I have monthly average chemistries coming into that. And also for the mine dewatering chemistries, I also have monthly average chemistries. There's one more element here, and this is a discrete change element. Because at the start of the simulation, you want to have some sort of chemical mass, which is in this case, the pond. So I have taken an initial chemistry, which is just a simple vector with a single set of concentrations for each component in that vector. I've multiplied that initial chemistry times the initial volume of water in the pond. So if you multiply milligrams per liter times volume, which would be something like liters, you get milligrams. And I set the trigger on this to an auto trigger. So when the model activates, it will add, actually, you could do either one actually, because you're starting at time 0. It will add this mass of chemical, chemical masses to the pond. GoldSim will actually then take those chemical masses, divide it by the volume in the pond, and give us an initial chemistry. So you can see that this is actually linked back to that initial volume as well. So to actually start doing the mixing calculations, we need to combine the chemical inputs from each one of our components of the water balance into another cell pathway, which represents the chemistry of the pond itself. So I'm going to put in another cell pathway here, and I'm going to name it cell pond, and I'll call it the bulk mix, because this is before equilibration with Phreeqc. I'll move this over to the side. In this particular case, we want the volume in the pond to be referring back to our pool element, which is named pond volume. See if I can find that here. I'm going to check these two boxes here because I want to save the final concentrations, and also I want to see the concentration histories for the pond. I'm going to change this to cumulative input as well. I'm not sure you really have to do that, but as a matter of fact, I normally do that. And then I'm going to define the inflows into this pond, and we need to have one inflow defined for each one of our water balance components for the water types that enter the pond. So the first one is precip. So I'm going to add an inflow from the cell that's called cell precip chem. And the rate at which it comes in is equal to the pond direct precip. So if I close that out and I looked back up here, you can see now we've connected the water balance into our chemical balance, at least for that particular element. So I'm going to go back in here again, and I'm going to do the same thing for the inflows. I need to add an inflow from the tailings. So from the tailings cell pathway, I'll select it. And then I will add in its water flow. This is how GoldSim calculates the mass or the chemical load coming into the pond and multiplies the flow rate times the chemistry that's contained in the cell called cell tailings chemistry, and adds that into the pond so it mixes with everything else which is in that pond. Finally, I'll add the flow that comes from the waste rock. And that flow is equal to the waste rock runoff flow. I'm going to go back to the definition, and then I'm going to also add the initial chemical mass, which you can add with the discrete changes. And there's only one in this model, so that's easy to find. So I'll close that out. And now we have defined the mixture of water which goes into our pond before I add some more elements here to equilibrate it. But there is one more thing that I do need to do before I take that step. And if we look at our water balance, you can see we have water going in. In other words, we have 3 inflows coming into our pond. But we've also got 2 outflows, and we need to account for their effects on chemistry. Well, the effect of evaporation is automatically taken into account because evaporation removes water, but it does not remove chemical mass. At least it shouldn't. But we also have another outflow, and that's the water which is pumped to the tank. So if the water was pumped to the tank out of the pond, the chemistry which is dissolved in that water would go with that water to the tank. So it would actually leave our system and enter the tank. So in our cell pathway down here, we actually have to represent that. If I ran the model now, you would see the concentrations in this cell pathway just increasing continuously because there's chemistry going in, but there's nothing going out. So we don't actually care that much about this bulk chemical composition. So I'm actually going to add another cell pathway, and I'm going to call it a sink. And that's just a name you can use. I don't think it's required, but I'll call it the sink underscore pond. You can give it whatever volume you want because this is basically a black hole that you're sending the chemistry into. I will set this to the cumulative input, and then I will specify the inflows coming from our cell pond bulk mix. And the rate of flow is equal to the demand out of the pond. So you can find that if you put in pond volume, put in a period, and then you can find its outflow. Of course, you can do the same thing by going to, if I go to insert link, and if I find that pool element named pond volume, I can click on the outflows and select pump to tank. What this will do, this will send the chemical mass that would be going to the tank and just send it into this sink so that it goes out of our system. So now if I put in, I'll just put in a time history, and I will just look at something like calcium and maybe sulfate. So I'll expand this and I'll go into our cell. And if you expand this, and then you can see there's an entry called concentration in water. If you expand that, then you can pick whichever chemical component that you want to show in the time history. So I picked calcium and sulfate. So I'll run the model here and we can check the result. You can see that we have sort of some fluctuations in the sulfate and the fluctuations in the chemistry, but they look about right according to what I know about the chemistries of our inputs, in particular the tailings in the waste rock. Well, I should mention that the tailings water is sort of alkaline, the waste rock is acidic. So we're mixing in the precip chemistry, which is a minor component, is about neutral. But we're mixing basically a flow of alkaline water with a flow of acidic water. So we would expect to have some reactions going on as they mix together. I should also mention too, I often name my cell pathways with the name cell first. And the only reason I do that is when I'm looking for them, they're all grouped together alphabetically. So it just makes them a little bit easier to find. But now I'll get into the part that maybe is of most interest, and that's how to link up with Phreeqc. So to do that, I'm going to add, I'll go to functions, and I'm going to add what's called an external element. And I'm going to name this pond Phreeqc. Just to indicate that this is doing the connection. The next thing we need to do is we need to define the DLL path. So if we click here, we can look for that DLL path, and basically this just refers to the name of the dynamic link library. The file filter here is actually looking for the extension of .dll, and the extension for the Python DLL actually is .pyd. But if you just put in asterisk here, hit return, you can find everything which is in your folders. And so here's the actual dynamic link library. This is something which is installed when you install the GoldSim Python interface. It will install this for you. If I actually went to my file system, you can see they actually go into a directory called bin, and there's a 32-bit version of the .pyd file and a 64-bit one. I'm using the 64-bit one in this particular case. So I've got the path set up. Then you also have to give it the function name. And this is the function within the dynamic link library, which allows you to communicate with that library. And its name is GSPy with a small y. This actually is case sensitive because Python names are case sensitive. Then it's called interface. Then you also want to check run in a separate process. So this will run outside of GoldSim. And once these things are set up, we need to go to the interface. And this is where you define what goes into the external element. In other words, what is going to be sent out to Phreeqc. And then what comes back is the output back to GoldSim. So if I click plus here, this would be the what goes out to Phreeqc. And what we want to send out to that is actually the chemistry, which is in our bulk mix of the pond. So if I expand that, and I expand this, you can see this is the chemistry here. So if I just pick here, the concentration in water and say, okay, you can see GoldSim will pick the entire vector of species, which will be contained with this name, with the name of the cell pathway, and then the name concentration in water appended to it. So I'll say okay. So that's the inputs. In other words, this is the data which is going out to Phreeqc. Next, I will define what's coming back from Phreeqc. And I'm going to call this EQ just to refer to the equilibrated concentrations. In the setup that I'm using, I have programmed it to use milligrams per liter. And then you want to tell it, of course, that it is a type of vector with the name of species because we are working with chemistry here. So this is all you have to do at this point to get this set up to work with the Python interface. So I'll say okay here. And before I'll put in another result or time history element here so that we can get some results out of the pond that are equilibrated. So I'll just pick pH and aluminum. So if I expand this and then go to add results, I can go to my external element and I can pick the different outputs that I want to see. So I'll pick pH, and then I will also pick, in this case, aluminum. So I'll save this here in case I make a mistake. Now I'll run the model. And right after I run this model, I'm going to open up the Python code, and we'll take a quick look at that. You can see before I added this external element, the model ran in less than a second. And now it's going to take somewhere around 18 or 19 seconds. So there is a cost in time when you do this sort of calculation with Phreeqc. If I double click on the results, we can see we have some results for pH in aluminum. You can see when the pH is low, the aluminum concentrations are high. When the pH goes up, the aluminum goes down. And as I'll show it in just a minute here, the reason for this behavior is that I have equilibrated this solution with the solubility of aluminum hydroxide. So aluminum hydroxide has what's called amphoteric solubility. So it has high solubility at low pH and low solubility at sort of neutral pH, and then solubility goes up again in alkaline pH. So something that all geochemists know about. Same thing you would expect for iron and iron hydroxide. But you can see it appears to be working correctly, that we're getting concentrations which mimic the solubility of aluminum hydroxide. So I'll set this back to edit mode for the moment and save it. And now I'm going to open up the Python code. And I'm using Spyder, which is a development interface which you get with Anaconda. And the great thing about this is free. I've used a couple of other ones. IntelliJ I really like, but it does cost money. I know a lot of people use PyCharm, so you could use that as well. But for the most part, I've been using Spyder most recently, and it seems to work fine. Now, when you install the GoldSim Python interface from the model library, it will automatically install a file called the GSPy-Module.py. And the workflow when you're making changes is that you should probably work with a file with a different name, because the dynamic link library will only work with a Python file with this name. So you can see here, I have a working file name here, which that's really small font, but I've given it the name here of GSPy module _ Phreeqc, and then it looks like it has a date of last week. So this is my working file. If I make changes to this file, I'll actually have to save it and then rename it back to GSPy module.py, because that's the name that our dynamic link library, which is called GSPy.pyd, is expecting. The other thing is that this particular file has a structure that you need to follow. And that structure has a series of different functions with these names. And so these functions all need to be in your Python file. So if I scroll down a little bit, the first thing you can see what I've done is I'm importing the PhreeqPython library of functions. That's the library that you get when you install PhreeqPython. There's not a lot of documentation that comes along with that installation. So the best thing to do is actually open up the source code for that, and then you can see all of its functions. But if we skip down a little bit, there's a couple of important things here. One is the number of inputs, and one is the number of outputs. The number of inputs in this case is exactly equal to the number of species in that vector back of the GoldSim model. If you remember, that had 21 entries. And so you have the number of inputs coming into this file is 21. And in this case, I've got 21, in other words, 21 different concentrations for each one of the components of the species vectors being returned back to GoldSim. If we scroll down here, there's a few other necessary functions. You don't really need to do much with those unless you want to add maybe some error checking. But then we get down to actually the real meat of the Python code, and that's the do calcs and return values function. It receives you can see this is sort of a star args sort of input sequence as a list, a Python list. And so there's some manipulation of those lists which is going on in this code. And I'm not going to explain all of this. If you're a Python programmer, hopefully this will make sense. But in fact, a lot of the code that's in this source code, actually what it's doing is it's resolving the names of these species IDs which are used in GoldSim compared to what's used in Phreeqc. In GoldSim, you can use things like underscores and parentheses, like if you wanted to put in sulfate, you would put it in as S, and then parentheses 6 or +6 to indicate the +6 valence state. But GoldSim cannot use a parentheses, or cannot use a negative sign or a plus sign. So a lot of the code here is actually sorting through the names of the species and then converting them either to what Phreeqc can use, or then reconverting them back to what GoldSim needs to have. But if we scroll down a little bit farther, we can see now in this what's called this inputs dict, which is a dictionary, a Python dictionary, I'm starting to build the input to Phreeqc. So this is just a starting point. So I put in the units, I put in the temperature, I've given it an initial pH, but I've given it also the designator of charge, because I want Phreeqc to calculate the charge based on the equilibria. I've also given it a PE as the starting point, which is the default oftentimes of 4.0. To be honest, this is probably not needed because I'm also equilibrating the solution with atmospheric oxygen. So that's going to get overridden anyway. And Phreeqc is going to calculate the PE based on oxygen and the pH. Then here's an important line right here. Actually these two lines. These are going to take the list of the species IDs and the concentrations coming from GoldSim, and it's going to zip them together to create a dictionary. And then the next line is actually going to append these concentrations to where with the starting point up here, it has these first 4 initial lines. And this is very similar to the solution keyword definition in Phreeqc. In fact, I'm going to go to TextPad here for just a second. If you looked at sort of a standard input to Phreeqc, this is an example. You have a solution keyword, and then you have a definition with units and all the different options. And then you have a list of concentrations, followed by, in this case, equilibrium phases as another keyword, where I have equilibrated the solution with aluminum hydroxide, iron hydroxide, and gypsum, with a saturation indice of 0 and an initial amount of 0 moles per liter. And then also with atmospheric amounts of oxygen and carbon dioxide. So the solution sort of definition here is following that same format to create the first part of that input file. The next line, which is important, is this one right here, which instantiates an instance of PhreeqPy, which starts up an instance of Phreeqc Python. In this case, I have told it to use the WATEC4.dat thermodynamic database. When you install PhreeqPython, it actually will put in a few databases for you, but it did not include this one. So I've copied this from my Phreeqc installation over to the location. My location is actually here. It's an Anaconda, lib, site packages, PhreeqPython, and then database. And so I'm just using a relative file path here to tell PhreeqPython the database that I want to use. This one actually adds our solution now that we've defined it with that instance of the PhreeqPython object. And then this next line here actually is doing that equilibration. So this is equivalent to using the equilibrate phases keyword in Phreeqc. You can see I designated 3 solids, and then atmospheric oxygen and carbon dioxide. So this goes in as a list of lists, I guess. So we've got the names, then we've got the initial, or actually the saturation indices and the partial pressures. Then we have the initial molar amounts. The next bunch of lines are actually converting the return values from Phreeqc back into something that we can send to GoldSim. And so finally down here, the results are going to GoldSim. We've got a couple of lines which are just converting the molar concentrations for the different elements that are in our species list. It's converting them back to milligrams per liter. So it's dividing by the gram formula weights, multiplying by 1,000, and then sending them back. Oh, and I should mention, I'm also putting in that results back to GoldSim in the last position, using the last position of that Python list, I'm putting the pH. And this is the pH coming directly from our equilibrated solution. So there is a function in the PhreeqPy solution class which allows you to just get the pH. So I'm putting that at the end, and this is the reason that I have pH at the last position of the species vector, because I want to get this value coming back from Phreeqc. It just seemed easier to have that as the last slot in that vector. Before I go on, I'm actually going to change this file a little bit just to show you how this works if you were doing this in practice. I'm going to uncomment a couple of lines here, which I'm going to get the saturation indices, because there's also a function here called .si, where I can get the saturation indices back for different mineral phases. In this case, aluminum hydroxide, iron hydroxide, and gypsum. And I'm going to append those back onto my results going back to GoldSim. So I'm going to add 3 more results to what's getting sent back to GoldSim. So if I do that, then I actually have to go back up to the number of outputs and change this to 24. And now I'm going to save this. And I have to now go to my file system and go in here. And actually, I'm going to delete the original GSPy module. And I'm going to copy this one and then rename it to GSPy module, because, of course, this is the name that the dynamic link library will work with. And this is a bit of a, maybe a sort of a problem with this approach, in that you only have one file to work with in that single name. But that's maybe a minor thing, because you can see there was no compilation needed. I just needed to change the file and then rename it, and that was it. But if you remember, I've added 3 more entries onto to what's coming back to GoldSim. So I also have to, in the output definition, I need to add 3 more entries to represent those saturation indices. So I'm going to add one for the aluminum hydroxide. I'll just call it AL and ALOH3 for the first one. I'll add another one for iron hydroxide, so I'll call this SiFeOH3. And the last one, I think, was gypsum. So I'll add one for gypsum. So now if I wanted to get results for the set, I go to insert element, results, time history. I'll call this pond, I'll call it TH, pond, SIs. We can expand that same external element, because it now has these extra entries of aluminum hydroxide, iron hydroxide, and then finally the saturation indice for gypsum. So I'll say close this, I'll save it, I'll run this one more time, we can see those results. And there it's done, and we can double click on this, and then now we can get those saturation indices. Oftentimes, this is something of interest in a chemical model, and you can see the iron hydroxide and occasionally the aluminum hydroxide has reached the solubility limit, so the value is 0, and the rest of the time it's somewhat undersaturated. So I'll go back to edit mode, and now I'm going to expand this model, because remember, we've got this extra tank over here, then we want to actually put it into the model as well. So I'm going to add another contaminant transport or cell pathway element. I'll call this cell pond EQ chem. And you can give this any sort of arbitrary volume here, because this becomes sort of like a chemical source that we're using. It has a defined concentration, and that defined concentration is what's coming out of our pond element, or our Phreeqc element, which is pond Phreeqc and dot, and the equilibrated concentrations. So now we've got those defined, and now we want to mix that in our tank with our mine dewatering chemistry. So I'm going to move this over here just to sort of get everything in the same view. I'm going to add another cell pathway, and I'll call this the cell tank bulk mix. And in this particular case, it's going to refer to the volume of water that's in our tank. Now I'll turn on the time histories. I'll switch this to cumulative input. And now we'll have our inflows. We have one that's coming from the cell, from our mine dewatering chemistry. So I'll pick that one first. And its flow rate is equal to the mine dewatering flow. And then we also have a flow coming from our cell, which is called the equilibrated chemistry that's coming out of this cell pathway. And because this chemistry is coming from the pond, it's actually equal to the amount of water which is being pumped from that pond into our tank. So we also have water that's leaving our tank as overflow, so we have to account for that as well. So I'm going to copy this sink, put it over here, and I'll call this the sink for the tank. And then I will specify its inflow is coming from the tank bulk mix. And the rate of inflow is equal to the tank overflow. So that connects us back up to our water balance for the tank. And then finally, I'm going to add in another external element, just like this one, to equilibrate the chemistry in the tank. So if I go to external, and I'll call this tank Phreeqc. We need to get our DLL path in there again. So there's our .pyd file, and then we need to tell it to be GSPy interface. Run in a separate process, and now we need to define our interface. In this case, what we want to go in is what's coming out of our tank. So I will get its concentration. And then we need to define what's coming back. So I'll call this the tank. Well, actually, I'll use the same name because it's going to be prepended anyway. Milligrams per liter. And the type is of course, a vector with the name of species. Now, one of the things to consider is that we actually have 24 different results coming back from our external elements. So I actually need to add in exactly the same things again. That is those saturation indices. So I'll give them the same name again. So there's the first one. Saturation indices are logarithmic values, so they don't have any units. So I'm not putting any units in here. And finally, SI. If you don't do this, GoldSim will automatically stop and say, it'll tell you, say, hey, you're telling me that, like, if I did not make these last three entries here, and I only had the 21 different values coming back in the vector, GoldSim would stop and say, hey, you've got 21 values coming back, but the Python file is telling me that it's got 24. So automatically you know that it's checking and you have to make these changes. So I will put in another time history here just to look at the saturation indices in the tank. So this time we want to get them out of our tank as well. So there's the last one, and I'll say close. And now we've got basically everything set up. And I'm going to save this and I'll run it one more time. And you'll notice this time it'll take about twice as long. And that, of course, is because we're running PhreeqC twice as many times. So now we're running PhreeqC for every time step, so 730 times, and we're doing that twice. So there's a lot of information going back and forth between GoldSim and PhreeqC through this Python interface. One thing I have noticed is that this is faster than the C++ method that I have uploaded previously to the model library. The Python also is a little bit more convenient in terms of there's no need to recompile, but it's a little bit less flexible. You don't have quite as many options on the solution chemistry as you do with C++. Here's the results for the tank for the saturation indices. For the first, at the start, they're sort of undefined, so it's got a really small number. I'll just set this to -10, and I'll make the maximum 5. And here we can see those saturation indices. So it looks like gypsum never quite reaches saturation here, and it looks like aluminum and iron hydroxide sort of intermittently reach saturation, so they have a value of 0. So that's basically the model that I wanted to show. So I'm going to stop here, and I think we have a couple of minutes for questions, and I've got time after the turn of the hour if the questions go longer than that. So Jason, I will turn this back to you because I'm not sure if I can actually see the questions if they pop up.
Yeah. So one question was, did you include pH with units of milligrams per liter so it could be included in the chemistry matrix? I saw this a little bit late. I'm not sure if you covered that already.
Oh, yeah, no, that's a good question. Yes, I did. You kind of have to give it some sort of concentration. And if you look, actually, I'll go back to edit mode here just quickly. If you look at, if we just open up one of these things, you can see the pH does have milligrams per liter because that's the default for everything in the vector. It's the same thing with these more complicated chemistries. You can see everything has units of milligrams per liter. So it's kind of meaningless for pH, but you have to work with that as the input. So I hope that makes sense. And that to me, that's always been kind of a confusing thing. But the way that I've structured the Python file to make pH last, it makes it easy to manipulate it in a Python list because it's always the last entry in that list. So that was the logic behind having that set up that way.
Okay, thank you. Another question that came in earlier was if you were going to upload any more files to the article that talks about this model. And I remember yesterday you said that you might include the source files that weren't included before. Is that right?
Yeah, I forgot to mention this. I'm gonna switch over here to Spyder. When I was working on this, it was pretty confusing trying to get it to work because there's not a lot of documentation for PhreeqPython. So I actually wrote some code here. I'm going to switch to that. You can see I just have to have at the top here, import PhreeqPython. this code actually sort of simulates the entire process of the connection. And I wrote this code to try to understand how to do the functions that are in the actual Python connection. So I can make this available. I found this really useful. If you run this code and you look over in the console window, you can get all of the outputs you want, so you can check things to make sure they're working correctly. And so that's what I've done here. You can see I've got lists, so I've got manipulation of the characters in those lists. I'm testing all of that. I've got concentrations. I have sort of some examples. This would be just like what was coming from GoldSim. Then I've got the construction of that dictionary that gets input to PhreeqPython. And then I've got a series of things here which output and print out concentration, so I can check to make sure it actually worked correctly. This is really useful, and if anybody wants it, I'll try to make sure it can be uploaded to the model library, or if you email me, I can send you a copy. So this is one file we can add. And if you want the model file that we worked on today, Jason, I don't know if you put those with the webinars or not, but I can certainly send it out if anyone wants to send me an email about it.
Yeah, no, I was planning on getting those files from you and updating that along with posting the recording of this like we usually do. So yeah, those files will definitely be available there. That shouldn't be a problem. And let's see. Another question is, I may have missed it, how does precipitation of solids work in terms of the balances? Do you have solid phases in the mixing cells, or have the ability of species in solution to move out of solution and back again?
Yeah, that's always a kind of a problem. It's more difficult in this approach. It's a little bit easier in the C++ approach. But if you wanted to do that here, you can see by the fact that what I did was I actually separated out, and right now I'm showing the chemistry portion of this model. You can see by putting in the sink here, I basically sent all of the chemistry down here out of this bulk mixing cell. And so coming into here is just basically this mix. So you have the equilibrated concentrations here. So if you actually wanted to determine how much precipitated, you'd have to take the chemistry from this one. Say if you wanted to look at the amount of gypsum that was precipitated, you'd have to take the bulk concentration of gypsum, or of something like calcium, might subtract the equilibrated concentration of calcium, then multiply that by the ratio of, well, basically the molecular weight of gypsum divided by the molecular weight of calcium. So you'd have to do this sort of outside of these connections. And that's the quickest way that I've been able to figure out how to do that. So that's, if you've done this sort of approach before, that's sort of a standard way to do it. If you're using the C++ method, you can actually program it to actually probably return that back from Phreeqc, but that's a little bit more involved. I don't think there's a function in the Python or the Phreeqc Python interface to actually get that back out of Phreeqc in this approach. Yeah, then the other limitation in the PhreeqPython approach is I don't think there's a way to define a surface. So I don't think you can have adsorption as a consideration if you're using PhreeqPython. The C++ method does allow you to do that.
Okay. Okay, next question is, what happens when you do not use the run in separate process option when coupling Phreeqc?
Good question. I don't know. I don't think I've tried that. I think the key thing is you want, I'd be a little bit afraid that you might have some problems with the causality sequence in GoldSim, because GoldSim, and I'm not totally sure about this, so I'm making sort of an educated guess, is that if you send out as a separate process, it probably runs asynchronously, so it's kind of in its own universe. And GoldSim is going to wait for its results to come back before it moves on to the next calculation. So I suspect it could cause some problems there. I've not thoroughly tested that, so I don't know that for sure, but that would be my guess.
Great, thank you. All right, is there anything else out there? I don't see any other questions. So I think that might be it, Ted. All right, well, it looks like there aren't any, but if you do have follow-up questions, as we've already mentioned, you can follow up with either us, I can point you to Ted, or you can ask Ted directly at any time. I think, Ted, I think your email address, if I'm not mistaken, is in that article in which we've uploaded the model. Anyway, if you want it there, I can put it there.
Yeah, it's showing here right now too, if anyone wants to jot it down.
Yeah, you guys can see it there. Okay, well, if there isn't anything else, thank you very much for joining. This was very informative, very interesting, and hopefully you guys can all join us next month. If you want to be on our email list to where we give announcements each month for these webinars, please let me know and I'll add you to the list. Thank you very much, Ted, for giving this this webinar and taking the time to do it. It was very nice.
Yeah, and thanks everyone for listening, and good luck with Python.
All right, thanks everyone, and I'll end it now.